So before we actually start, I would like to ask everyone a question, whether you have seen this movie called Wreck-It Ralph. I think I'll be able to see people's like videos along the side. So if you know, if you watch this, please raise your hand, let me know, or having some thumb up.
I have seen Wreck-It Ralph.
Great. So it seems like I know people somehow know this movie. It's great that so when we discuss like the situation in the movie, you'll probably have some background knowledge, you have some understanding of that. So so basically in this movie, uh, this Rocket Ralph is like a character living in a virtual world. He looks like this, and in this movie, has a very special capability of jumping to different games. For example, he can decide to jump into a very like realistic first-person shooting game called Hero's Duty, and once he jump into this world of like first-person shooting, and he will immediately transform into like a soldier, like a Rocket Ralph, so that he will fit into, for example, a large group of army. And he also, and sometimes he decided to go to like an old school game like Dixie Felix. And because it's like an old school game, everything's like 2D, pixelated. And if we jump into this world, he will immediately transform into this kind of pixel style Rocket Ralph. And this is actually something that's very interesting and very important for the future of internet, basically metaverse, because we in the future we may have so many virtual world, and you may jump into this world for today and jump into that world for the other day. And if you let's imagine if you decided to let's say, oh, I just want to play the old school Super Mario game developed in 1990s or something like that, and if you just jump into this world and be like a very realistic like 3D characters like this, it is a little bit strange that you will feel that I'm not belong to this world, and now probably just I forget it and just jump into another world. But let's say if there's a stylized version of you where you can just translate it into this kind of pixelized style, then immediately you'll feel that you more belongs to this world and you're more belongs to this game. So actually, this kind of scenario, at least this Wreck-It Ralph, is very inspiring to me. It basically indicates the importance of creating some stylized geometry. So instead of just having yourself, you probably have a bunch of stylized version of you in order to fit into different scenarios. And if today you want to, I don't know, create a stylized version of you, probably what you will do is you will open some 3D modeling software like ZBrush, Maya, Blender, anything, and start cranking these kind of all the tools there or subdivision, all kinds of things to create a stylized version of yourself. And in this video, you're seeing like a professional artist basically using these tools to create a character. And you can see that it is actually very, very difficult to use. You're still involved a lot of low-level operation of individual vertices, individual faces, and it is very, very difficult for people without professional training to do so. And if you want to get a feeling of how difficult that is, what the basic means is just like the 2D analog of like the previous video is basically creating an image by manipulating the pixel one by one, until you get an image you like. So you can imagine if this is the only way that we can model 2D images nowadays, I don't think you'll be posting images or figures on like Twitters or on Instagrams on a daily basis. So in today, we are going to basically take a look at the problem of 3D stylization. Basically, we want to have some faster way of taking for example, like a realistic geometry as the input, and we're able to stylize it like without a lot of efforts into something that can fit into certain scenario. But before talking about like what the technique we worked on, first let's have an interesting discussion on what is a style. And style is, to me, is a very interesting thing to think about because it's something that's very abstract and not very well defined. And even if you ask people from different communities, they will have their own answer and they are very different from each other. So actually, when we think about stylization, it's very important, at least to me, to think about, okay, if I want to do stylization, what do I mean style? And personally, my favorite definition is this one proposed by Eric Fernie in 1995. It basically says that the style is a distinctive manner which permits the grouping of different works into related categories. So basically it means that if there's a certain rule you can follow to classify a bunch of artworks into different categories, then this rule you follow could be considered as a definition of style. So it means that there are multiple definitions. They are not a single definition, but this way is like a way that we can define the style. So it will be better to have a visual example, right? So let's start by looking at this a bunch of images. Okay, and in this case, if I want to do classification into two categories, one of the solution could be classify these images into these two categories. And you can see that for the images on the left, they share the similar color palette here. But for the images on the right, they do not share the similar color palette. So it means that if I classify these images into these two categories, the elements that we use to kind of do this kind of style classification is the color of the image. So in this case, the element of style for these images can be a color. But we are not going to talk about image processing today. We're interested in 3D stylization. So you may ask me, okay, I now understand that color is a pretty good style element for images, but is there any good style element for geometries? And the answer is so, but yes, because actually in a lot of architectural literature, people have tried to think of some style elements for geometry so that they can classify buildings coming from different countries or coming from different centuries into categories. And there are definitely a lot of definition of these kind of elements of geometric styles, but there are three ones that are very popular. The first one is going to be the shape. And shape is I know this is a little bit vague, but it basically means that if these two buildings, the subcomponents share a similar shape, then these two buildings can be considered as the same style. For example, these two buildings can look at the rooftop, they look more like this kind of a water drop kind of shape, right? And the second component people use quite often is the proportion, which is, I think, easy to understand. And the third one people looking at is the characteristic lines or characteristic curves living on this kind of geometry. For example, these two red lines, they share similar shape in these two curves. And these three components are very popular in terms of classifying those buildings into different styles. And it is also popular in graphics to build discriminative models to tell style similarity. For example, given this query building as the input, by analyzing the similarity of the three components we talked about, we are able to have an algorithm quantifying, okay, the building in the center is more closer, it's more similar to the building on the left, and the building on the right is less similar by basically analyzing the three components. But the next question I would like to toss out to you is that, okay, but how about generative models? Can we utilize those three elements to turn, for example, bunny into a style of this kind of green cone geometry? And first, personally, I feel like this is very difficult, at least when I first try to think of, how I can, by analyzing the characteristic curves, how can I kind of turn bunny into this, something like that. To me, it is actually very challenging, but I won't say this is impossible. Perhaps in the future, they'll have some great algorithm that turning this into possible. But for me, it is actually very challenging right now to utilize those geometric style elements to do generative models. So it motivates me to think, okay, because style is there's no a single definition of style, there are actually multiple definitions, but is there some style definition for geometric style that is easier to understand for computers and it's easier to create generative models? So this boils down, so the answer of this question boils down to the main thing of today, where I want to talk about three different directions we explored during like the past few years. And the first is the style of rendering and the style of geometric learned prior. And the third one is the style of surface normals. So let's start with the first one, which is, I would say, the most natural option built on top of a lot of interesting image processing or image stylization filters today. So right now, after decades of image processing research, we have so many great algorithms to capture the style of paintings or capture the style of images. And for example, one of the most representative one is the neural style transfer, where you take this image as an input and you pass through a pre-trained image CNN, and the image is able to extract some kind of more like a low-level features about the colors or the strokes of the painting, which represent the style of this painting. And if we have these kind of elements available, then we can build an energy E that measures the similarity between a pair of images. For example, in the bottom left example, these two images are less similar by comparing those style elements, but the image pair on the bottom right, they are more similar. So basically, we have a lot of tools like this that are available to us to analyze the style of images. And if we want to generalize those or leverage those definitions to 3D geometry, the natural way to do is to define the style energy for the geometry using the style of its rendering. And we can define the style of rendering across multiple views so that we can have like a more like a global analysis of the style of a 3D shape. And this is the first kind of a direction we explore. And this can lead to an optimization algorithm that that's driven by rendering or driven by images. So basically, the goal here is that we start with a 3D shape and whose rendering will correspond to some very high style energy value. It means that it's not a good stylized image. And our goal is basically to figure out what is the output geometry whose rendering will correspond to will correspond to a very low style energy value. It means that we kind of stylize this geometry so that its rendering can minimize the style energy. And this is basically the goal we want to achieve. And this could be done with a differentiable rendering. Basically, the overall pipeline is that we start from a 3D shape like this V, and we first render this geometry into an image like this one. And we can perform some image processing or image optimization to get some modified, manipulated image like this one on the top right. And the last step is to utilize something called a differentiable renderer to kind of transfer those image changes back to 3D. So for this differential render is basically a tool that can give us the derivative of the individual pixel colors with respect to the vertices. So it basically tells us that, okay, if I want to make the image like this, how I should move the vertices in this 3D space. And this could also differentiate with respect to colors and other things, but here we focus on differentiating through the geometry, basically the vertex locations of the 3D. And if we do this process kind of iteratively, we are able to do something like this. Right, and the underlying image we use here is some image energy that try to make sure the image is piecewise constant. So when you translate to 3D, it corresponds to piecewise planar geometry, and you can see that we can immediately get a piecewise linear patches on the 3D shape. But you also notice that, oh, but this is not really 3D stylization. You're only optimizing like a part of the geometry. We want the global stylization, right? So, but actually generalizing to multi-views is also very simple. So basically the process you saw earlier, you only need to do for multiple views during the optimization. So what it means is that for iteration 1, we sample a camera, render into an image, and run this kind of image processing and then a differentiable renderer to modify the geometry a little bit. And for the next iteration, we sample another camera, render another view, and go through the process. And we basically go through this kind of stochastic, more like a stochastic gradient descent for all the iterations until we converge. And if we do this, then we can easily turn this geometry into like a global stylization using the same filter we saw earlier. And we are definitely, because this is something that only operates on the rendering of the geometry. In other words, we only operate on images. So we can actually use a lot of image filters or image processing algorithms that are available out there. For example, we can just plug in those superpixel algorithm, and this is a result we can get. And definitely, we also, the most interesting things to try stylization, right? So we also try.
Question from the audience.
Yes. Yes. What's the question?
Sorry, I was wondering about how you liked the 3D object during this operation, because that should affect the result, because that affects the image itself, right? So how do you pick the lighting?
That is a perfect question. So I skipped this part because of the time reason, but this is a really, really great question. So I would say the rendering affects a lot, and basically a lot of time in this when we work on this project, we spend on analyzing what is the renderer we want to use here. And the short answer is that actually in our algorithm, it's like a 3D input a 3D mesh, and output is also a 3D mesh. So actually, the intermediate rendering appearance does not matter. We don't need to use any fancy photorealistic or like those shiny, or like basically we don't need to use a very photorealistic renderer. We just want something that can faithfully represent the geometry. And faithfully, I mean that, for example, in terms of a shading model, we don't want to use garage shading or found shading, which kind of smooths out the geometry. We want to use something like flat shading, which if the geometry is not smooth, then we can immediately see this effect in the rendering. So actually, after all sorts of experiment, we end up noticing that the simplest possible renderer that you implement from your intro to computer graphics course is the best one. So we use like flat shading, directional light, all sorts of like simplest component as possible, and make it efficient and differentiable and render this. But yeah, I can happy to go through all the details of the experiment with you offline. But yeah, this is basically the renderer we use here, and that's a great question.
And then that biases the kinds of styles that you can actually reproduce.
Yes, and that also influences the style we can reproduce. For example, I would say the one of the limitations for working on image domains is that they are not every image style has a 3D version. Like, because for example, if you're just optimizing the vertex locations, if there are just certain image styles that are described by solely the color of the image, like color palette, then in this case, color is not a variable that we optimize for. So it is actually very difficult to get a 3D geometry that has a certain color style, and that's basically just impossible. So yeah, there are definitely interesting discussion on what are the 2D kind of image filters that can be translated to 3D, and that will also relate it to how we render the geometry. Because let's say if we render geometry with textures and then we optimize with respect to textures, then for those image style with colors, we can definitely achieve that. So it's really a design choice.
Thanks.
No problem. Yeah, thank you, Ed. Yeah, just like for the rest of the talk, feel free to interrupt me like this. I'm happy to answer questions at any time. So yeah, so basically what we talked about earlier also works for image style transfer. So in this situation, we run the neural style transfer here, where the top right shows our style image. And you can see that because we optimize the geometry, so we are not capturing the colors, but we are capturing this kind of circle patterns, and you can see those patterns appear on this geometry. So basically means that, okay, style is actually a very kind of valid way to define style of a 3D shape. And besides this, there are also a lot of other works, especially recent works on this topic. For example, this kind of artistic neural field is also like an image-driven kind of 3D optimization, but instead of optimizing for the vertices, they optimize for the kind of neural implicit functions in the scene. But I won't go into spend too much time on this. But I would say there are a lot of a long line of work that are very interesting along this direction. But the second question I would like to ask you is that we are still actually working on like this 3D domain. We are creating 3D meshes, and it's sometimes actually limited or unsatisfying if we have to go through the length of the renderer and then differentiate through the rendering process. For example, one limitation is the performance. Like, for example, if you want to optimize the 3D geometry to have certain style, you have to go through multiple views to render this. And there are also some internal structure of the 3D mesh. They're just very difficult to put, render inside and look at, all the angles. So if you want to optimize the geometry from the rendering perspective, it can achieve certain effect, but there are also some cases that are just actually not really satisfying, especially the performance. So the next question I'm thinking about is like, okay, can we actually learn a geometric style directly? For example, I give an input bunny to like, whatever network, and whether we are able to extract those style elements from this geometry so that we can translate this style elements into different shapes. So, and also in order to think about how we can do this, we take the inspiration also from the image processing community. So basically starting from like the image on the left, typically for the image processing people, they will separate the style and the content as two different components. And for the content, they usually consider those large scale elements. For example, in this painting, we have the moon, have the mountain, these kind of thing. And this can be considered as the content, basically what's inside this image, basically the content of the image. And the style in this situation are usually defined as those kind of small scale strokes or colors in this image. So if we follow this kind of a definition, how can we generalize this to 3D? So let's say if the input is no longer an image, but it's a 3D mesh, and a large scale content could be defined as the low resolution counterpart of that mesh. Basically, it's like a low frequency, large scale content of the shape. And whatever that's left, like the difference between this input green shape and the content shape, then this is something that we hope to capture, and we can treat this as a definition of like a geometric style. And to follow this kind of idea, this motivates us to think about motivates us to kind of formulate a neural subdivision or upsampling problem, where the input is like a low resolution content geometry. And our goal is to train a neural network that will upsample this geometry for us, so turning this content shape into something that's very high resolution. Okay, and our goal is to minimize the difference between the upsampled shape and the ground truth shape that has both the content and the style in it. So basically, the idea is that starting with the content geometry, we want a neural network to add the style back into those content so that it end up match the ground truths we use to, for example, generate those content shapes. And in order to train this network, the first thing we have to talk about is definitely, okay, where we can get the training data of LiDAR, and how should we design the network, and how should we define the loss function. Basically, these are the three things we need to ask ourselves every time when we start a machine learning project, right? And so first, let's discuss a little bit about the training data. So ideally, because we want to have a lot of ground truths and then the content, and then their difference will be the style. So ideally, we really hope to have a large number of pairs of low resolution input and some ground truth output. And the difference between them will be the style we want to capture. But unfortunately, there's no such kind of a training data available out there. So we have to think about different ways that we can supervise this network to train. So the idea we come up with is to use self-supervised training. So basically, we start by taking a high resolution shape as the input. This is something that's available. There are more and more 3D data sets offline, so you can easily grab a shape, like the high resolution shape here, and put it as a ground truth. And then what we can do is that we can use the off-the-shelf decimation algorithm to randomly simplify this ground truth shape into many low resolutions. And you can see that this bunny are decimated into many coarse bunnies with different triangulations. And then can take this low resolution bunny as the input to the network, and this network will output an upsampled version of that input. As you can see that we have more triangles, more vertices here. And we define the network in a way that we can actually recursively apply the network several times. So until we reach that we want to reach the subdivision level 5, and we treat this as an output level. And then we will compare that output bunny with respect to the ground truths that we use to generate the input shape. And this way we have basically we have a new loss function to define the difference between the two, and then we can easily backpropagate those loss functions to kind of update the network, and then to get to minimize the network, to kind of optimize the network so that we can minimize this loss function. Okay, and today I won't have time to go through how we define the loss function, but I would like to talk having like a short deep dive on how we define the network here. So if you look at this, just like zooming this picture, you'll notice that, okay, the input of our network is a 3D mesh, like a triangle mesh, and the output of the network is also a triangle mesh. So, but learning on 3D meshes is actually something that's not that trivial. At least it's very difficult back then. And because like a 3D mesh has so many natural variations. For example, taking this rocker arm in the middle. A 3D mesh can have the same resolution. It means I have the same amount of vertices, but it has a different triangulation. But you can see that they are both representing the same shape. And the 3D mesh can also have a different resolution. It means that different number of triangles, different number of vertices, but they are still representing like the same shape. And the 3D mesh can also be translated or rotated like freely in the space, and they are also exactly the same shape. So if you want to define a machine learning architecture onto a 3D shape, it is actually very important to consider how we can define the networks in a way that it can handle all these different variations. And another reason why doing mesh-based learning is a little bit difficult is because a lot of machine learning operators, for example, like the convolution we want to use for the image CNN, now they are not so easily to generalize to like mesh convolution. For example, if you just want to follow this naive idea, like we do convolution on pixels, and let's say we want to do convolution on vertices, then one immediate problem you'll notice is that for this vertex, it may have like 6 neighbors, but for other vertices, it may have like 5 neighbors or 7 neighbors. And it means that when you want to define a convolution filter, on image domain, we can say, oh, we define a 3x3 filter, but on vertices, oh, it is unclear like how we should define the size of the filter. So basically means that there is a direction that's still very, at least, it's not like readily applicable for today's architecture. Perhaps it will be in the future, but right now it's basically not a solution here. So a lot of people, whenever they want to do 3D learning, they are considering alternative representation. For example, like a triangle mesh, you may consider as a block turning into voxels, and it's become like regular structure. You can do convolution building there, but you can see that it is a poor approximation of a 3D shape, right? And some people may consider like graph neural network and use a graph neural network to learn on 3D shape. And I would say this is like a perfect valid approach, but you lose a very important information. You don't know whether this is the graph of a social network graph or this is a graph of a triangle mesh, which has a very specific structure that it approximates the surface and 3 edges forms a triangle. So basically lose this kind of structure information, which we can leverage to make this learning architecture better. And some people may also consider point cloud, but this is even kind of more challenging than graph because you not only lose the manifold information, you also lose the connectivity information. So there are some point cloud method, you have to kind of infer the connectivity of points in order to do the learning. So in this work, we are not going to use these kind of approximation, but instead we want to do learning on triangle meshes directly. And the key idea we leverage here is to do convolution on something called a half-length, which is basically 2 triangles associated to each half edge or directed edge, like the edge with direction. Okay, and if you look at this half-lap, you'll notice that, okay, there are actually a few advantages you can see already. For example, if you want to do convolution on vertices, and if you focus on half-lap, it is very nice that each half-lap will always have 4 vertices. So it means that if you want to define the CNN, you know that the kernel size, you can define the kernel size as 4. And another cool thing is that these 4 vertices actually has a canonical ordering from black, blue, green, and red. So basically it means that, okay, if you want to define convolution, we also know that, for example, image domain, we know this is the first pixel, second pixel, third pixel, or something like that. And in this half-life, we also have this information. And this is extremely important to have a canonical ordering because it allows us to define a local coordinate system, which is the key to make our network rigid motion invariant. So in order to illustrate this, I'll have a toy example here. So let's imagine you want to train like a neural subdivision network and where you want to use the vertex location as the input features, okay? And we can train a network to subdivide this cow at this location. Okay, and after training, everything's perfect, we minimize the loss. But imagine during the test time, if we rotate this cow just slightly rotated, and if you apply the same network, this is the result you will get. And the reason is because although from human perspective, we know that these 2 cows are exactly the same shape, just different orientation, but this rotation will also change the vertex coordinates. So if this is the input feature to the network will feel like, oh, these two shapes are completely different because all the features are different. So it will have difficulties to generalize to different orientations. But if we have the local coordinate system, all we can do is very simple. We just do a coordinate transformation to represent our vertex locations using this local coordinate string. And once we do this, then no matter how we rotate or translate this cal, the input feature remains exactly the same. So it means that if we train this neural network using this local coordinate system, then suddenly it will become a rigid motion invariant. In other words, if we rotate this cal and subdivide it with exactly the same network, we can get a perfect upsampling result like this one. So this is basically how we handle the orientations. But how about resolutions? So the way we handle resolution is by how we define the architecture of the network. So in this architecture, it's greatly inspired by those classic subdivision approaches. So basically, the first step is to do topological upsampling. So it basically means that for each triangle, we split it into 4 triangles so that we have more vertices, more faces, but we do not change the geometry at this moment. We just like for each triangle, we split into 4. That's it. And the next step is the interesting part. So the next step is that for each half flap, we pass those half flap features into a neural network. And the output of the neural network is going to be a displacement vector. And then we'll then copy paste this displacement vector to our mesh. Okay. And we'll move on to another half flap in the mesh. And again, pass this through the network, which may give us a slightly different displacement vector, but we can still put it back to the mesh. And we'll do this process for all the half flaps in the mesh. So imagine after this process, you'll have many displacement vectors for all the vertices in your model. And then what we'll do is do a global average pooling to get a single displacement for each vertex. And then we can use this kind of displacement to actually move the displace or change the geometry. And this process can be actually done recursively. So you can see that this new mesh, we can also do the same thing, do topological upsampling and pass through the half flaps. So we can actually recursively doing these operations of multiple iterations until we reach our desired level of subdivision. So once you understand this procedure, you'll notice that I did not make any assumption on what's the input number of vertices, what's the number of half flaps in the mesh. Basically, if you define this network operation locally, then you are naturally supposed to handle different input with different resolutions. So basically, that's how we can get the model work on different resolutions. But how about triangulation? Like the same shape can be triangulated differently. How can you ensure that your network is robust to this? And this is that we cope this problem by the way we generate training data. So instead of taking a single ground truth shape and we run the deterministic simplification to decimate into like a one version, we actually run randomized simplification algorithm so that during the training, the network already sees hundreds of bunnies triangulating a different way. So, and you can imagine if we learn on like a large collection of these shapes, then our naturally learns how to robustly handle shapes with different triangulations. So that's basically how we handle triangulation. So, and basically this is basically help us to at least have some robust solutions to handle these kind of natural shape variations. And let's take a look at some results.
Hey, Derek, before you get into
yes.
that, just a brief question, and maybe this is something for sense to follow up on offline, but I know I'm not intimately familiar with any of the details, but I know that recently there's been 1 or 2 works that have proposed tessellation and variant learning on surfaces. And I wonder if you've looked at any of those and whether you feel like those are compatible with this framework, so you could sort of avoid this problem of having to do this random data augmentation.
Yes, this is a great question. So I would say this problem, how I should interpret this. So I'm not sure which exactly word you're referring to, but for example, Nix has a diffusion work, but there are also some works like the delta conf that are coming out this year, but there's also a lot of work that try to do intrinsic shape learning, and they define the convolution or like the way we think about it, do message passing through, for example, the diffusion process, the kind of thing. So that if we know how to do diffusion on different triangulations, we can naturally support like robustness towards different tessellation. But I would say the downside of those things is that there are one thing you have to be aware of, because a lot of those methods, they are defined purely intrinsic. In other words, like if you have a human with different pose, they can give you exactly the same output. But for the generative models, intrinsic properties may not be exactly the thing you want, because you may want to know how this object sits in the space, and how, if you want to do like upsampling or some generative task, how you should based on like the extrinsic information to know how to upsample this geometry. So I would say those architecture, if you think of it as a way to do convolution in a way that's robust to tessellation, it's a great approach, and I really hope to try this out in this framework. But one concern is that you have to somehow modify this approach a little bit so that you can have a better way to be aware of those extrinsic different information. I would say it's not impossible. So I would say it's a very interesting thing to try, but you have to be aware of like the difference between intrinsic and extrinsic properties.
Yeah, I'll follow up with you on this later, because
Yeah.
I don't yet quite see in my head an example of where you would definitely want to have extrinsic information to do proper stylization, but we'll talk about it.
No problem. Yeah, happy to talk a little bit more. Cool. Other questions before we move on to the result? Okay, so we can jump into the result right now. So let's say after we go through how we do design the network or things like that, then we can definitely give it and train a network and throw it out to try out to upsample a lot of different shapes. For example, these are the input shape we tried, and you can see that they are very different from each other. But when we apply our network, the surprising thing is that, wow, if we apply our network to upsample all these shapes, they are actually generalized pretty well in terms of, for example, preserving those eyes or those fine features of these kind of different creatures. And we wonder, okay, this seems like it's generalized pretty well, but you must need a large collection of shapes to train on, right? But the answer is no. In order to, when we train on just a single shape and test on all these examples, surprisingly, it works pretty well in terms of generalizing to different shapes. And besides this experiment, we also try to learn on a single pose and test on shape in different poses. In this case, the same story happens. We can also get like a good generalization to upsample all this geometry into different outputs. And the fact that we only need the single shape or like a single pose to train is very, very, very exciting for us, at least to me. It is because when we have the input shape here, the user can provide just a single shape to this framework, and because it's just a single shape, so this could be a shape with certain style. For example, we dump into the elephant with like a smooth geometry everywhere, so it means that we want something smooth, and the network is able to know that, oh, based on the single trained data, we want to output something that's smooth. So given this input shape, after this neural network upsampling, we can get a smooth output chair out of it. But if this time we provide a more like man-made object with sharp creases, flat faces, this kind of thing, and you can see that those kind of corners or flat faces are preserved from the input shape after this upsampling. And again, you can also test out, okay, if we dump into some, noisy shape like this one, and as expected, after the upsampling, we can get a noisy chair as output. So it means that based on our definition, like an early definition of the separation between content and style, the network is able to kind of extract what is the style by a single training shape. And you can use this as a way to, okay, we dump into different shape, and the network learn something from this shape, and we can kind of transfer the style to different geometries. So that's basically conclude this part. And any questions so far? Yeah, we just have some questions, but if not, I'll jump to the third part, which is another exciting topic I would like to talk about today, is the style of surface normals. So in this line of work, our goal is to not using machine learning, which seems a little weird, but we really want to think whether we can capture the style by cracking out an equation that describes some style. I will go back to this equation later, so you don't need to think about what this equation is talking about right now. So basically, the goal is to figure out an equation that describes certain style. And in order to do it, the first exercise, at least I did, is by open up Google and then search all these kind of sculptures and then staring at for the entire day. And after this kind of process, I actually noticed that there are a lot of cubic sculptures that are very popular across art history. For example, like this one, they are like coming from different countries, coming from different centuries. And if you look at these cubic sculptures, you'll notice that, hey, artists tend to preserve those details like hairs, the eyes, eyebrows, and things like that, so that we know that what's the underlying content of the shape. But if you step back and zoom out and look at the global appearance, you'll notice that these sculptures, they look like a generalized version of a cube. So it means that if we want to reproduce these cubic sculptures, this is what we want to achieve. We want to preserve the details of the geometry. We want to make like a general appearance look like a cube. So it basically motivates me to think about this question. How can we characterize the style of a cube? Basically, staring at this single cube, how can you define the style of this cube? And perhaps the first idea that pop up your mind is to say, we can look at the vertices. It's obvious that if we look at the cube, each vertex always share like 3 90-degree corners, and this is my definition of cube. Yeah, I would say that's a valid one, but when I tried this out to transfer this definition to stylize a bunny, this is the algorithm I created to cubify this bunny. And you can see that based on this definition is a very good stylization. That this bunny, they have like almost everywhere there are some 90-degree corners, vertices there. But if you look at this cubic sculpture we saw earlier, I don't think you'll agree that we kind of successfully achieve the job. Basically, the better approach here is to take this bunny and we're able to stylize this way where we preserve the details, but the global appearance looks like a cube. So, and the key idea we really achieve that is to not characterize the cubic style using vertices, but instead we utilize surface normals. Basically, if we look at the cube, the surface normals are going to be axis aligned, means that the vector could be 0, 0, 1 or 0, 1, 0, or more basically things like that. And once we have this observation, and things becomes better right now, because right now we have more and more mathematical tools for us to achieve this. For example, the one we use here is the L1 norm, because we know that the L1 norm of an axis aligned vector is going to be smaller than the L1 norm of a non-axis aligned vector. So basically, it motivates us to come up a energy that for each vertex, then we try to minimize the L1 norm of the normal vectors of the output mesh, so that when we minimize this energy, we can make it as an axis aligned. And in addition to this term, we also want to preserve the details of mesh, right? So we also add another regularization that try to make sure the input is the same as the output. And this is achieved by the as rigid as possible optimization. And I'm looking at the time. I feel like we may not have time to go through each terms. So allow me to skip through it to go to the point I want to make later on. So basically, if you don't know as rigid as possible, it's completely okay. You just know that this is a term that can preserve the details of the geometry. But one thing that I want to point out is that this energy itself is actually very difficult to optimize because of this term. Because the normal vector of the output mesh is actually a nonlinear function. So it means that this term itself will make the entire energy a nonlinear energy, which makes it very, very difficult to optimize efficiently. And so the way the trick we do here is to perform a change of variable. We say that instead of optimizing the normal vectors of the output, we optimize the rotation times the normal vectors of the input mesh. And you may ask why I can do this. Can I just change the term to whatever I want? And I would say in this case, the answer is yes, because each unit vector, let's say in 2D, each unit vector can always be represented as a rotation times another unit vector. So therefore, in this case, we can approximate this output normal vectors as a rotation times another normal vector. And we choose it to be a normal vector of an input because it is a constant throughout optimization. So once we do this, then the entire energy becomes linear, and it is very easy to optimize and without skipping through the optimization part. But basically, at the end of the day, we have an algorithm. By minimizing the energy we talked about, we can achieve a stylization look like this. And because this is just a single energy optimization, so it's super efficient, that we can already have a interactive tool to optimize the geometry. We can also have a lot of artistic controls. For example, we can have different cubeness. This is a less cubic bunny and super cubic bunny. And we can also have different orientations to cubify this geometry from different like axes. And we can also add constraints. For example, in this case, I constrain the 4 legs to lie on the two planes, and so that I can make a table cleaner showing on the right. And one thing I also want to mention is that we can actually do things more than a cube. So in this case, we can achieve this by analyzing using like shape analogies framework. So basically, starting from this sphere and this style, we want to achieve like this A-plane, this cone. And let's say user give us another shape like this B. And our goal is to figure out what is this B-plane by analyzing the relationship between A and A-plane. And the way we achieve this is exactly the same. It's very similar to the cubic stylization where we analyze the surface normals. So for example, the first thing we do here is to analyze the relationship between A and A-plane in terms of how their surface normal change. And so that once we understand the relationship, the next thing we do is to transfer this relationship to change the surface normal from B to a target normal on the B-plane. And I know this normal is not the actual normal, it's just like a target normal we want to achieve. And once we have this, then the rest of the step is just to optimize the geometry of B-plane so that the actual surface has the actual normal that align with the target normal. So once we have this, then we can easily generalize the cubic stylization to styles more than a cube. For example, in this case, we just the gray shape are the B, like the input user want to stylize, and those green shape are the A-plane you saw earlier, basically the style shape we want to achieve. And by doing this, we can easily stylize different geometry in a different way. And this basically means that so right now we can have another easy to use stylization algorithm using shape analogies. By providing different shapes and analyzing the relationship against the cube, then we are able to stylize this cow in many different ways. Any questions for this part?
Super cool.
Thank you. Yeah. Okay. So I want to still save some time for the Q&A. So let's quickly jump into like what's next. So I would say, although I'm working on like stylization for like quite some time, but even today, I still think that this is still at the very beginning of 3D stylization. Like decades of research have put it into 2D to 2D image stylization, and also a lot of research are dumped into 3D to 2D, those kind of non-photorealistic or stylized rendering. But really, 3D to 3D stylization is just something that's just started to emerge. It's not a lot of algorithm out there that can achieve this. And I would say there's not no algorithm. There are some algorithms for specific style, including the one we talked about today. Basically, given this input, they have some target style in mind, and they can create like a tailor-made algorithm to make to stylize geometry in that way. But I would say there's not really no work that can do generic geometric stylization. For example, in the record route example we saw earlier, that we can turn it into every style we want. And I really believe that if we want to achieve a generic stylization algorithm, like one important thing we have to think about is how can we develop a robust AI generative models. And the reason is because we all know that, like, for example, perhaps in the next 3 or 5 years, all of our cell phones will be able to scan 3D object, perhaps even a high quality 3D object. So it's very easy to foresee an explosion of dirty or 3D data in the wild in the next few years. And it's really important for us to develop robust machine learning architectures so that when those data is available to us, but they are dirty, but no one's going to clean it, and we are still able to leverage this amount of data to do some interesting learning on it. So I would say this is what I think is very important to prepare for the future. And I would like to thank all the collaborators for the project mentioned today. With this work will not be there without their help. And also thank you all for listening. And I'm happy to take any questions. Yeah. I'll just do stop sharing so I can see the face bigger.
That sounds good. All right. Any questions from the audience? Either here or over Zoom?
I'll pause as somebody else wants to.
I can start with mine if.
Sure, go for it, Guy.
Yeah, so I'm wondering, kind of a lot of the work kind of assumes that you're using like the triangle mesh representation, which when we're talking about stylization or kind of like actual the transformation process, this is probably not the representation used by many of the designers in creating those. So do you think that there is something that you can do here to kind of like using kind of a more upstream representation when doing this kind of stylization? Do you think that will help, or any thoughts on that?
Yeah, this is a great question, and this is also a question I've been thinking about these days. Basically, I would say, okay, just list a few common representation. Like triangle mesh is good in terms of its efficiency, like perhaps the most compact way of representing 3D objects, but it's also hard to learn. It's like discrete, it's irregular, that kind of thing. And there are also some, for example, like implicit fields, and they are continuous and super easy for the network to optimize and to learn, but also suffers from, for example, if you give me a nerve, I don't think the current graphics pipeline is ready to render or processing, even deform those nerve models. This is still like an ongoing research. So, and there I can definitely go through a long list of representation, but right now I feel like in terms of representation, it really depends on the use case. If you are okay to just like visualize it as a static kind of object, like a lot of like nerve reconstruction, like we just want to visualize it, and I'm saying then you should think about using those, for example, implicit or neural fields kind of representation, which is more easier to optimize. But if you really have an application in mind, I want to use it in the downstream graphics applications, you may think of a different direction, either optimizing on the representation that the network is good at and turn it into a classic representation, or you can try to think of whether we can do learning or stylization on those classic representations, for example, like a triangle mesh talk about today, or even quad meshes, because a lot of designers are using quad meshes. So yeah, I really love this question, and I really hope to see there breakthroughs in the future on either, for example, merging these representations or having some breakthrough in triangle mesh learning so that we can do a great learning on triangle mesh or quad meshes. Yeah.
Other questions? I'll ask a follow-up to Kai's.
Okay. Yeah. So since you mentioned three kinds of style, shape, proportion, and lies, so
Yeah.
I wonder, any method work on the proportion style, and do you think it's a more challenging than just shape style for neural network? Yeah.
So let me make sure I understand your question to say whether there are work leveraging the proportion of the shape to do stylization. Yeah, there's a work about that. I can point out to you offline. But basically, but this thing is actually limited and actually very simple. You can imagine, for example, if I don't have an example here, but let's say I have a chair that just taller, like a leg is longer, and have a chair that's just like a shorter. And if we want to do stylization, like by only analyzing the proportion, we can just make this chair longer, and that's it, and we call it a day. And there are definitely all stylization you can do if you only care about the proportion. But there are some kind of research has to be done in terms of like making this proportion more be a general stylization algorithm. For example, let's say you want to stylize the bunny and want to make it into style of a giraffe, and you analyze the proportion. Okay, then how we should stretch the shape or deform the shape in a reasonable way so that it still looks like a bunny, but perhaps have a super long ear or like super long neck or something like that. So I would say this is an interesting problem because a lot of those shapes, lines, or those proportions, they are designed for buildings or furniture, so it's man-made objects. So if you want to do stylization in those ways, it will be more realistic. It will be more reasonable approach to take there. But for organic object like animals, that kind of thing, I would say it's not so clear to me. How can you, by analyzing the proportion or like those components, like to kind of have this style definition? So I would say I don't think it's impossible, but I would say there are works to utilize proportions and shapes to do like furniture, that kind of stylization, but not these kind of thing for organic shapes.
Okay, I see.
Yeah.
Thank you.
No problem. Thank you for the question.
Well, we're about 1 minute from the hour, so maybe we should wrap up for now. So let's thank our speaker one more time.
Thank you everyone for joining.